Here's a question nobody wants to answer. What if we're stuck? We've sent 9 successful missions to Mars, rovers, helicopters, orbiters, but return something from the surface? Never happened. Going to Mars is the easy part, but coming back is a completely different beast. If you love exploring humanity's biggest cosmic challenges, make sure to subscribe to this channel. Now let's get started. Imagine you're standing on Mars. The sky above you is a butterscotch haze. The temperature is around -60 degrees Celsius. The air pressure is less than 1% of Earth's atmosphere. You're standing in a place where the gravity is only about 38% of what you feel right now. And you need to leave. You need to build a rocket, launch it, rendezvous with a spacecraft in orbit, then fly that spacecraft across 100 million kilometers of interplanetary space, through the cosmic radiation, through the solar wind, timing everything perfectly so you arrive back at Earth when the planets align just right. And you need to do all of this without the massive infrastructure we have here on Earth. No launch pads, no fuel trucks, no mission control down the street. Welcome to the most difficult logistics problem humans have ever attempted. Let me break down why this is so brutally hard and why some of the smartest people in aerospace engineering are genuinely questioning whether we can pull this off anytime soon. Let's talk about gravity wells. Think of them like actual wells, the kind you might draw water from, except instead of water, you're climbing out using rocket fuel. And the deeper the well, the more fuel you need. Earth sits at the bottom of a deep gravity well. That's why it takes a rocket the size of a building, like the Saturn V that sent astronauts to the moon, just to escape Earth's gravitational grip. The Saturn V weighed nearly 3,000 metric tons at liftoff. Most of that weight was fuel. And even then, the spacecraft that actually went to the moon, the Command and Service Module plus the Lunar Module, represented only a tiny fraction of that original mass. Mars has a shallower gravity well than Earth. The red planet is smaller, less massive. Its gravity is just 1/3 of ours. So you'd think launching off Mars would be easier, right? Well, yes and no. You still need to achieve orbital velocity. On Mars, that means accelerating your spacecraft to roughly 3.6 kilometers per second just to reach a stable orbit. For comparison, orbital velocity around Earth is about 7.9 kilometers per second, so Mars requires less speed. But here's the catch: you need to bring all the fuel, all the rockets, all the equipment to Mars first. And that means launching all of that mass from Earth's much deeper gravity well. NASA engineers call this the tyranny of the rocket equation. Every kilogram of fuel you want to use on Mars needs to be launched from Earth. But launching that fuel from Earth requires even more fuel, which requires more fuel to launch that fuel, and so on. The math spirals exponentially. A 2023 white paper from NASA's Architecture Concept Review examined this exact problem. They found that the mass requirements for a round-trip human Mars mission, when you account for the nested gravity wells of both Earth and Mars, create what they describe as a mass multiplier effect. Essentially, for every kilogram of payload you want to land on Mars and then launch back off, you might need 10 or 20 or even 50 kilograms of mass at Earth departure, depending on your propulsion technology and mission architecture. This is why Mars return missions aren't just scaled-up versions of moon missions. The Apollo lunar module that launched off the moon and returned astronauts to lunar orbit was a relatively simple vehicle. It only needed to carry 2 astronauts for a short journey, and it benefited from the moon's incredibly shallow gravity well. Lunar escape velocity is only about 2.4 kilometers per second. Plus, the Apollo astronauts had a massive support infrastructure back on Earth, just 3 days away, and they brought everything they needed with them from Earth. Mars is different. Mars is months away, not days. The communications delay alone is between 4 and 24 minutes one way, depending on where Earth and Mars are in their orbits. You can't phone home for help. You can't abort back to Earth if something breaks. And you certainly can't bring enough fuel from Earth to land on Mars, do science for weeks or months, and then launch back off. The numbers simply don't work. The rocket would be too big, too heavy, too expensive. So what's the solution? This is where In-Situ Resource Utilization comes in, ISRU. It's one of those NASA acronyms that sounds boring, but represents something genuinely revolutionary. The idea is simple, almost elegant. Instead of bringing fuel from Earth, make it on Mars. Mars has resources. The atmosphere is 95.3% carbon dioxide. There's water ice beneath the surface, confirmed by multiple missions, including the Mars Odyssey orbiter, the Phoenix lander, and more recently, observations from Perseverance. If you could extract that carbon dioxide, split water into hydrogen and oxygen, you could manufacture rocket propellant right there on the Martian surface. The most commonly discussed ISRU approach is called the Sabatier reaction. It's a chemical process discovered back in 1910 by French chemist Paul Sabatier. You take carbon dioxide and hydrogen, run them through a catalyst like nickel at high temperature, and you get methane and water. Then you can split the water via electrolysis into hydrogen and oxygen. The oxygen becomes your oxidizer, the methane becomes your fuel, and you recycle the leftover hydrogen back into the Sabatier reactor. Sounds perfect, right? Chemically, it works. We've tested this process on Earth. It's proven technology. But here's the reality check. Nobody has ever built a fuel production plant on Mars. Nobody has ever demonstrated ISRU at the scale required for a human return mission. And the engineering challenges are staggering. Think about what you'd need. You'd need power. Lots of it. Splitting water and running chemical reactors requires enormous amounts of energy. On Mars, solar panels work, but they're less efficient than on Earth because Mars is 50% farther from the Sun. That means you get less than half the solar energy per square meter compared to Earth orbit. And Martian dust storms can block sunlight for weeks. NASA has been exploring nuclear power as an alternative. Fission reactors could provide steady, reliable energy regardless of dust storms or the Martian day-night cycle. In early 2026, NASA announced a mission called Space Reactor 1 Freedom, an ambitious attempt to test a nuclear reactor in space by late 2028. The plan involves adapting a Department of Energy research reactor design, one originally built for ground use, and grafting it onto a spacecraft bus originally designed for the Gateway lunar outpost. The timeline is aggressive. Building a space-rated nuclear reactor normally takes a decade. NASA is trying to do it in about 2.5 years. The challenges are immense. Research reactors on Earth sit in concrete-shielded buildings with abundant cooling water and human operators nearby. A space reactor has to survive launch vibrations, reject heat in a vacuum, operate autonomously for years, and never, ever leak radiation into the crew habitat. The engineering required borders on science fiction, yet it's the kind of technology we absolutely need if we're serious about Mars return missions. And power is just the beginning. You also need equipment to extract water from Martian soil or ice. You need compressors to pull carbon dioxide out of the thin atmosphere. You need storage tanks rated for cryogenic temperatures. You need pumps, valves, computers, sensors. All of this has to work reliably in an environment where the temperature swings between -125 Celsius at night and maybe 20 Celsius during the day at the equator, where dust gets into everything, where there's no technician you can call to fix a broken pump. A 2015 NASA technical paper titled Mars ISRU for Production of Mission-Critical Consumables outlined the state of the art for these technologies. The conclusion? ISRU is feasible. We understand the chemistry. We understand the engineering principles. But the technology readiness level for most of these systems is still low. We haven't built flight-ready hardware. We haven't tested these systems in actual Martian conditions. We have a lot of laboratory experiments and computer models, but laboratory experiments don't account for everything that can go wrong on another planet. And here's the truly nerve-wracking part. An ISRU fuel plant needs to work perfectly the first time, because if your fuel production system fails on Mars, the crew can't come home. There's no backup, no rescue mission. You're betting everything on technology that's never been proven beyond Earth. All right, let's zoom out for a second and talk about what this means for actual missions. NASA's Mars Sample Return Program was supposed to be the proof of concept. The plan was elegant in its ambition. Perseverance would collect samples and seal them in tubes. A future mission would land on Mars, deploy a small rover to collect those sample tubes, load them into a rocket about the size of a telephone pole, and launch that rocket into Mars orbit. Then an orbiter would capture the sample container and fly it back to Earth. No crew, no ISRU, just a relatively small rocket carrying about 500 grams of rocks. Guess what happened? In January 2026, the United States Congress effectively cancelled the Mars Sample Return Program. The reason? Cost and complexity. By 2024, an independent review board had projected the full mission cost at around $11 billion, with sample return potentially slipping into the 2040s. That's $11 billion and 2 decades just to bring back half a kilogram of rocks using a rocket that doesn't even need to carry humans. Let that sink in. If we're struggling this much with an uncrewed sample return, how are we supposed to launch humans off Mars? If you're wondering about the even bigger challenges we face, trying to travel between star systems, check out my video exploring the real reason we can't survive interstellar travel. Because the problems we're discussing today with Mars, as enormous as they are nothing compared to the physics-defying challenges of going to another star. It's on the card above and pinned on the comments. Now, SpaceX has a different vision. Elon Musk has been talking about Starship, a fully reusable spacecraft designed to carry up to 100 people to Mars. The plan involves launching multiple Starship cargo missions first, landing them on Mars and using them to produce fuel via ISRU. Then, when everything's ready, you send the crew. They land, refuel using the pre-positioned propellant, and fly home. It sounds incredible, and Starship is real. The vehicle exists. SpaceX has been conducting test flights, but here's the uncomfortable truth. A 2024 peer-reviewed paper published in Scientific Reports analyzed SpaceX's publicly available information about Starship Mars missions and concluded something startling. The paper, authored by researchers who examined mass budgets, trajectory optimization, and technology readiness, found that based on the limited information SpaceX has published, they could not reproduce a feasible Mars mission scenario. Even when assuming optimal conditions, a 100% recovery rate of crew consumables during flight, and everything going perfectly, the numbers didn't close. The system mass was too large. The propellant requirements were too high. There wasn't enough margin for a return flight. Now, this doesn't mean Starship can't work. It means SpaceX hasn't publicly shared enough details for independent researchers to verify the plan, and it highlights significant technological gaps. Power supply on Mars, for example. Starship would need enormous amounts of energy to produce the roughly 1,000 metric tons of propellant required for return to Earth. Where's that power coming from? How many solar panels? How much nuclear capacity? What's the backup if systems fail? These aren't small questions, and SpaceX itself seems to acknowledge the timeline challenges. In February 2026, SpaceX announced it was delaying its Mars ambitions by several years to focus on lunar missions under NASA's Artemis program. That's not a cancellation, it's a recalibration. But it signals that even the most ambitious private space company on Earth recognizes the mountain of engineering problems still unsolved. All right, we've covered gravity wells, fuel production on Mars, the collapse of NASA's sample return mission, and the uncertain status of Starship. But there's so much more to unpack. the propulsion technologies being developed, the competing international efforts, the human factors that make this even harder, and ultimately, whether returning from Mars is a problem we can solve in the next decade, or if it's going to take far longer than anyone wants to admit. So we've established that bringing anything back from Mars is extraordinarily difficult. But let's dig deeper into the technologies that might actually make it possible. Because despite all the challenges, engineers aren't giving up. They're developing propulsion systems that push the boundaries of what's physically achievable. Some of these technologies exist only on paper. Others are being tested right now in the laboratories and vacuum chambers, and a few might actually work. Let's start with chemical propulsion, because that's what we've been using since the dawn of the space age. Chemical rockets work by burning fuel and oxidizer together, creating hot expanding gases that shoot out of a nozzle at tremendous speed. Newton's third law does the rest. For every action, there's an equal and opposite reaction. The gases go one way, the rocket goes the other. It's simple, it's reliable, it's proven, and it's also fundamentally limited by the laws of chemistry. The best chemical rocket engines we have today, like the RS-25 engines that powered the space shuttle, can achieve what's called a specific impulse of around 450 seconds. Specific impulse is basically a measure of how efficiently a rocket uses its propellant. Higher is better. 450 seconds means you get 450 seconds of thrust for every kilogram of propellant burned. That sounds good, until you realize that getting to Mars and back requires carrying so much propellant that your rocket becomes mostly fuel tanks. This is where methane-oxygen engines come in. They're not more efficient than hydrogen-oxygen engines in terms of pure performance, but they offer other advantages. Methane is denser than hydrogen, so you can store more of it in a smaller tank. It's easier to handle, it doesn't leak through metal as easily. And most importantly for Mars missions, you can theoretically make it on Mars using the Sabatier process we talked about earlier. SpaceX's Raptor engine burns methane and oxygen, so does Blue Origin's BE-4. These engines are designed with Mars in mind, even if the full ISRU infrastructure doesn't exist yet. But chemical propulsion, no matter how you optimize it, hits a wall. The energy density of chemical bonds is finite. You can't squeeze more energy out of hydrocarbons than physics allows. So NASA and other space agencies have been looking at more exotic propulsion technologies that sound like science fiction but are grounded in real physics. Nuclear thermal propulsion is one of the most promising. The concept is straightforward. Instead of burning chemical fuel, you use a nuclear reactor to heat hydrogen propellant to extreme temperatures, then expand it through a nozzle. Because you're heating the propellant with nuclear energy rather than chemical combustion, you can achieve much higher exhaust velocities. Nuclear thermal rockets could potentially achieve specific impulses of 800 to 900 seconds, nearly double that of chemical rockets. That's a game changer for Mars missions, because it means you need roughly half the propellant mass for the same mission. NASA actually built and tested nuclear thermal rocket engines back in the 1960s and 70s under a program called NERVA, the Nuclear Engine for Rocket Vehicle Application. They ran 20 full-scale engine tests. The engines worked, they demonstrated the technology. Then the program was cancelled in 1973 due to budget cuts and changing priorities, but the knowledge remained. And now, 50 years later, NASA is trying to revive it. In January 2023, NASA and DARPA, the Defense Advanced Research Projects Agency, announced a partnership to develop and test a nuclear thermal rocket engine in space by 2027. The program is called DRACO, Demonstration Rocket for Agile Cislunar Operations. The goal is to build a functioning nuclear thermal engine, launch it into orbit, and fire it in space to prove the technology works. If successful, it would be the first nuclear rocket engine fired in space since the Soviet Union's experiments in the late 1980s, but nuclear thermal propulsion has challenges. The reactor core has to withstand temperatures exceeding 2,500 degrees Celsius, while hydrogen is flowing through it at high pressure. The materials science required is extreme. You need fuel elements that don't melt, don't crack, and don't release radioactive particles into the exhaust stream. And there are political and safety concerns. Launching a nuclear reactor into space makes people nervous, even though the reactor wouldn't be turned on until it's safely in orbit, far from Earth's surface. Then there's nuclear electric propulsion, which works differently. Instead of directly heating propellant with a reactor, you use the reactor to generate electricity, then use that electricity to accelerate ions to extremely high speeds using electromagnetic fields. Ion engines have been used on spacecraft like NASA's Dawn mission and several commercial satellites. They're incredibly efficient, achieving specific impulses of 3,000 seconds or more, but they produce very low thrust. We're talking about the force equivalent to holding a sheet of paper in your hand. That's enough to accelerate a spacecraft over weeks or months in the vacuum of space, but it's nowhere near enough to launch off a planet. So ion engines are great for the cruise phase between Earth and Mars, but they can't help you leave the Martian surface. You'd still need chemical rockets for landing and takeoff, then switch to ion propulsion for the long journey home. This hybrid approach is actually being seriously considered for future Mars missions. Use chemical propulsion where you need high thrust. Use electric propulsion where you need efficiency. There's also solar electric propulsion, which is the same idea as nuclear electric propulsion, except you generate electricity from solar panels instead of a reactor. NASA's Psyche mission, currently on its way to a metal asteroid, uses solar electric propulsion. The advantage is you don't need to deal with the complexity and political challenges of launching a nuclear reactor. The disadvantage is that solar panels become less effective the farther you get from the sun. At Mars's distance, you're getting less than half the sunlight you'd get at Earth. And during the journey, especially in the outer parts of the orbit, solar power drops even further. Now let's talk about something truly exotic: nuclear pulse propulsion. This is the concept where you literally detonate small nuclear bombs behind your spacecraft and ride the shockwave. I'm not making this up. In the 1950s and 60s, scientists and engineers working on Project Orion seriously proposed this. The idea is, you'd have a massive steel pusher plate at the back of your spacecraft. You'd eject a small nuclear charge, detonate it at a safe distance, and the plasma from the explosion would slam into the pusher plate, accelerating the ship. Enormous thrust, enormous efficiency. You could theoretically reach a significant fraction of the speed of light with this technology. Of course, it's also completely insane by modern standards. The engineering challenges are staggering. The political and environmental implications of detonating hundreds or thousands of nuclear weapons in space are obvious. And the Partial Nuclear Test Ban Treaty of 1963 essentially killed the project. But it's worth mentioning because it shows how far engineers have been willing to think outside the box when it comes to propulsion. When the physics of chemical rockets isn't good enough, you have to get creative. More recently, there's been interest in fusion propulsion. Fusion is the process that powers the sun, where hydrogen atoms are squeezed together under immense pressure and temperature until they fuse into helium, releasing enormous amounts of energy. If we could build a compact fusion reactor that works in space, we could use it to heat propellant to millions of degrees, achieving exhaust velocities far beyond anything chemical or even nuclear thermal propulsion could provide. Specific impulses could reach tens of thousands of seconds. Transit times to Mars could drop from months to weeks. But here's the problem: we still don't have working fusion reactors on Earth. Despite decades of research and billions of dollars invested, controlled fusion for power generation remains just out of reach. In December 2022, scientists at the National Ignition Facility achieved fusion ignition for the first time, where the fusion reaction produced more energy than the lasers put into it. That was a historic breakthrough. But it was a tiny amount of energy, a fraction of what you'd need for propulsion, and it required the world's most powerful laser system housed in a building the size of 3 football fields. We're a long way from miniaturizing that into a spacecraft engine, so realistically, for the next few decades, we're probably stuck with chemical propulsion for planetary takeoffs and landings, maybe nuclear thermal for the more ambitious missions, and electric propulsion for efficient long-duration cruising. It's not the Star Trek future we dream about, but it's what the physics and engineering actually allow. Now, while NASA has been struggling with budget cuts and program cancellations, there's been a surprising development on the other side of the planet. China is moving fast, really fast, and they might actually beat everyone to the punch when it comes to Mars sample return. In March 2026, Liu Zhizhong, the chief designer of China's Tianwen-3 mission, announced that the program has moved into flight model development. This is a critical phase where you stop building prototypes and start building the actual spacecraft that will fly. The mission is scheduled to launch around 2028, with the goal of returning at least 500 grams of Martian samples to Earth by 2031. If successful, it would be humanity's first Mars sample return mission. Not NASA, not SpaceX, China. The Tianwen-3 architecture is fascinating. Unlike NASA's cancelled approach, which relied on a single launch and tried to minimize complexity, China is going with a 2-launch strategy. They'll use 2 Long March 5 rockets, China's most powerful operational launcher. One rocket will carry an orbiter and Earth return vehicle. The other will carry a lander and ascent vehicle. Both spacecraft will travel to Mars separately, then coordinate in Mars orbit to transfer the samples from the ascent vehicle to the return vehicle. It's similar in concept to what the Soviet Union did with their lunar sample return missions in the 1970s and what China successfully demonstrated with their Chang'e 5 lunar sample return in 2020. They've proven they can do this kind of mission at the Moon. Now they're scaling it up to Mars. The key technologies they need to master include landing on Mars, collecting and sealing samples, launching off the Martian surface, performing orbital rendezvous around another planet, and returning through Earth's atmosphere at interplanetary speeds. China's chief scientist for the mission, Ho Zhengqian, published a detailed paper in Nature Astronomy in July 2025 outlining the scientific objectives. They're targeting Jezero Crater, the same region where NASA's Perseverance rover has been exploring, because the geology there suggests an ancient lake environment where life might have existed billions of years ago. The spacecraft will operate on Mars for about a year before launching the return mission. The entire campaign spans over 3 years from launch to sample return. What's remarkable is the speed and focus of China's space program. While NASA's Mars sample return ballooned to $11 billion and got cancelled, China appears to be executing their mission on a much tighter budget and timeline. Part of this is because they're building on proven technology from their lunar missions. Part of it is their centralized decision-making structure. And part of it is simply a different approach to risk. They're willing to accept a higher chance of failure in exchange for faster development and lower cost. If Tianwen-3 succeeds, it will be a watershed moment for space exploration. It will demonstrate that Mars sample return is achievable with current technology. It will provide the international scientific community with pristine Martian samples for study, and it will establish China as the world leader in deep space exploration. The geopolitical implications are significant. Space has always been as much about prestige and technological demonstration as it has been about science. But even if China brings back samples by 2031, that's still just samples. Rocks and dust. Bringing back humans is an entirely different challenge, orders of magnitude more difficult. Because humans need life support. They need food, water, air, radiation shielding, medical supplies. They need living space. They need to stay healthy and sane during a multi-year mission. And if anything goes wrong, they die, which brings us to one of the most terrifying aspects of Mars return missions: radiation. Space is filled with radiation, high-energy particles from the Sun, galactic cosmic rays from exploded stars across the galaxy, and there's nowhere to hide. On Earth, we're protected by our planet's magnetic field and thick atmosphere. Most of the deadly radiation from space never reaches the surface. We're cocooned in a protective bubble that makes life possible. In space, that protection is gone. Astronauts on the International Space Station still receive some protection from Earth's magnetic field, but even there they're exposed to radiation levels 10 times higher than on the ground. On a Mars mission, you're completely outside Earth's magnetosphere. You're exposed to the full brunt of cosmic radiation for months or years, and the consequences are severe. NASA has strict radiation exposure limits for astronauts. The current standard limits career exposure to a 3% increase in the risk of dying from radiation-induced cancer. That's the upper bound at the 95% confidence interval. For a Mars mission lasting around 900 days, including the 6-month journey there, a year and a half on the surface, and the 6-month journey back, astronauts would be exposed to somewhere between 600 millisieverts and 1,000 millisieverts of radiation, depending on solar activity and shielding. A 2013 study published in PLOS ONE by NASA researchers calculated that a Mars mission could result in radiation doses that push right up against or even exceed NASA's safety limits, and that's just for cancer risk. More recent research has identified other dangers. A 2021 study in the journal Aerospace examined what would happen if astronauts were caught in a major solar particle event during the mission. Solar particle events are sudden bursts of radiation from the Sun, usually associated with solar flares and coronal mass ejections. They're unpredictable and can deliver lethal doses of radiation in hours. The study looked at historical records of extreme solar events, including evidence of a massive solar storm in the year 993 or 994 AD, preserved in tree rings and ice cores. If a solar storm of that magnitude hit a spacecraft en route to Mars, astronauts could receive radiation doses of tens to hundreds of millisieverts in a single event, possibly causing acute radiation sickness and significantly increasing cancer risk. There's no real-time warning system that could give astronauts enough time to seek shelter. By the time we detect a solar particle event from Earth, the radiation could already be hitting the spacecraft. Shielding helps, but only to a point. You can surround the crew habitat with water tanks or other materials that absorb radiation. But the more shielding you add, the heavier the spacecraft becomes, which means you need more fuel, which means more mass, which triggers the rocket equation problem again. There's a balance between protection and practicality, and right now, nobody's quite sure where that balance point is. Mars itself offers some protection. The planet's atmosphere, thin as it is, blocks some radiation. The surface of Mars receives about 0.6 millisieverts per day, roughly half what astronauts experience on the International Space Station. So living on Mars is actually safer from a radiation perspective than traveling through deep space. But you still need to get there and back. All right, let's talk about something that might sound mundane, but is actually one of the most frustrating constraints on Mars missions: orbital mechanics. You can't just launch to Mars whenever you feel like it. The planets have to be in the right positions, and those positions only align properly once every 26 months. Miss your window and you're waiting over 2 years for the next one. This isn't a guideline, it's not a suggestion, it's the iron law of celestial mechanics, and it governs everything. Here's why. Earth and Mars orbit the Sun at different speeds. Earth completes an orbit in 365 days. Mars takes 687 days. Earth is closer to the Sun, moving faster. Mars is farther out, moving slower. As Earth laps Mars like a runner on an inside track, the distance between the two planets constantly changes. At their closest approach, called opposition, Mars and Earth are about 55 million kilometers apart. At their farthest, when they're on opposite sides of the Sun, they're separated by over 400 million kilometers. If you want to send a spacecraft from Earth to Mars using the least amount of energy, you use what's called a Hohmann transfer orbit. It's an elliptical path that touches Earth's orbit at one end and Mars's orbit at the other. You launch when the planets are positioned such that by the time your spacecraft reaches Mars's orbit, Mars will be there to meet it. It's like throwing a ball to a moving target. You don't aim where the target is now, you aim where it will be. The math works out such that the ideal launch opportunities occur roughly every 26 months. In the space industry, these are called launch windows, and they're not very wide. You typically have a few weeks where conditions are favorable. Launch too early or too late, and you need significantly more fuel. Launch outside the window entirely, and the mission becomes impractical or impossible with current technology. This means that any Mars mission has to be planned years in advance around these windows. If you're developing hardware and it's not ready for the next launch window, you're automatically delayed by 26 months. That's what happened with the European Space Agency's ExoMars rover. Technical issues and the geopolitical situation with Russia, who was providing the landing platform, pushed the mission past the 2020 and 2022 launch windows. The rover is now targeting the 2028 window at the earliest. 6 years of waiting because of orbital mechanics. For a return mission, the timing becomes even more critical. Once you arrive at Mars, you can't just turn around and come home immediately. You have to wait for Earth and Mars to be in the right positions again. That means astronauts would spend somewhere between 450 to 500 days on the Martian surface, not because they necessarily need that much time to do their work, but because the planets won't align for the return journey any sooner. Some mission planners have explored what are called fast conjunction trajectories, or opposition-class missions, which reduce surface stay time to about 30 days by taking a longer route home. But these require much more fuel, expose astronauts to longer periods in deep space where radiation is highest, and are generally considered less practical for first-generation Mars missions. So most plans assume you're going to be on Mars for at least a year and a half. That's a long time to be completely cut off from Earth in an environment that's actively trying to kill you. Speaking of which, let's talk about what it's actually like on the Martian surface, because the challenges don't end when you land. Mars is a desert world. The average temperature is about -63 degrees Celsius. At night, temperatures at the equator can drop to -100 Celsius. During the day, they might reach 20 Celsius in sunlight, but the moment you step into shadow, the temperature plummets. There's no atmosphere to retain heat. The atmospheric pressure at the surface is about 600 pascals, roughly 0.6% of Earth's sea level pressure. That's below the Armstrong limit, the pressure at which water boils at human body temperature. If you stepped outside on Mars without a pressure suit, the liquids in your body would start to boil. You'd lose consciousness in about 15 seconds from lack of oxygen. You'd be dead within 2 minutes. The environment is utterly unforgiving. Dust is another constant threat. Martian dust is incredibly fine, much finer than beach sand. It's more like talcum powder, and it gets into everything. solar panels, mechanical seals, zippers, electronics. The dust particles are also slightly electrostatic, so they stick to surfaces and are hard to brush off. During global dust storms, which can envelop the entire planet for months, visibility drops to near zero and solar power becomes unreliable. The Opportunity rover survived for 15 years on Mars, but finally died in 2019 when a global dust storm covered its solar panels and it couldn't generate enough power to keep warm. For a human crew living on Mars, dust contamination would be a daily battle. You'd need airlocks with multiple chambers to minimize how much dust gets tracked into the habitat. You'd need filtration systems to keep the air clean, and you'd need protocols for cleaning equipment and suits after every excursion. It sounds tedious, but it's critical. Martian dust might also be toxic. Studies have shown that the regolith contains perchlorates, chemical compounds that are harmful to humans if ingested. Breathing it in over long periods could cause serious health problems. Then there's the psychological challenge. Imagine being confined to a small habitat with a handful of other people for over 2 years. You can't go outside without a spacesuit. You can't call home without a 20-minute delay. You can't see trees, or feel rain, or smell fresh air. The horizon is always rust-colored and barren. The sun is smaller and dimmer than you're used to. You're farther from home than any human has ever been. NASA and other space agencies have studied isolation and confinement extensively. They've run simulated Mars missions where crews live in isolated habitats for months at a time. The HICS project in Hawaii, the Mars 500 experiment in Russia, and NASA's CHAPIA program have all provided valuable data on how humans cope with these conditions. And the findings are both encouraging and concerning. Crews generally adapt well if they're carefully selected and trained. Maintaining a routine helps. Having meaningful work helps. Communication with the outside world, even with delays, helps. But psychological issues do emerge. Interpersonal conflicts, mood disturbances, sleep problems. Some crew members experience what's called third-quarter phenomenon, where motivation and morale dip around the halfway point of a long mission. It's when the initial excitement has worn off, but the end still seems impossibly far away. On Mars, there's no emergency extraction. If someone has a mental health crisis, or if interpersonal conflicts escalate, the crew has to handle it themselves. Mission planners are acutely aware of this. They're developing psychological support protocols, communication strategies, and even considering how to design habitats to maximize privacy and personal space within severe volume constraints. But it's hard to simulate the true psychological pressure of knowing that you're utterly isolated on another planet with no possibility of rescue. Medical emergencies are another nightmare scenario. What happens if someone gets appendicitis, or breaks a bone, or develops a serious infection? The crew would need a member trained in emergency medicine, surgical procedures, and dentistry. They'd need a well-stocked medical kit with diagnostic equipment, medications, and surgical instruments, and they'd need to be prepared to handle situations that would normally require a hospital. There's been serious discussion about whether to include a trained surgeon on Mars crews or to train all crew members in basic medical procedures. Some mission concepts include telemedicine capabilities, where doctors on Earth guide the crew through procedures via video link, accounting for the communication delay. But that delay makes real-time assistance impossible. If someone is bleeding out, 20 minutes is an eternity. If you love understanding what it really takes to become a spacefaring species, please hit that subscribe button. This channel breaks down the science, the discoveries, and the beautiful impossibilities of space exploration. NASA has been researching autonomous medical systems, artificial intelligence that can help diagnose conditions and guide treatment. They've studied how wounds heal in low gravity and altered atmospheric conditions. They've looked at how medications degrade over time in space radiation. Every aspect of human health becomes a complex engineering and logistics problem, and then there's the return journey itself. After spending 18 months on Mars in 38% of Earth's gravity, the crew has to launch off the planet, survive another 6 months in zero gravity during the trip home, and then somehow be healthy enough to survive re-entry and landing on Earth. Bone density loss and muscle atrophy from reduced gravity are serious concerns. Astronauts on the International Space Station, even with rigorous daily exercise, lose bone mass at about 1 to 2% per month. Over a 2.5-year Mars mission, that's a significant amount of skeletal weakening. Current exercise countermeasures help, but don't completely prevent the loss. Mars crews would need even more robust exercise protocols, possibly including resistance training equipment that can work in Martian gravity. Some researchers have proposed pharmacological interventions, drugs that could help maintain bone density and muscle mass during long-duration missions. But these treatments are still experimental. We don't fully understand the long-term effects of reduced gravity on human physiology. When the crew finally launches off Mars for the return trip, they're climbing back into the radiation-filled environment of interplanetary space. They're exhausted. Their bodies have been weakened by months in reduced gravity. Their psychological reserves have been depleted by years of isolation and stress, and they're facing a 6-month journey back to Earth with no margin for error. If the life support system fails, if the propulsion system malfunctions, if a solar storm delivers a lethal radiation dose, there's no rescue. They're on their own. The final challenge is Earth re-entry. When you're coming back from Mars, you're hitting Earth's atmosphere at about 11 kilometers per second, much faster than returning from the Moon. The Apollo capsules re-entered at about 11 kilometers per second, and that was right at the edge of what heat shield technology could handle. A Mars return vehicle would be coming in at similar speeds, possibly higher, depending on the trajectory. The heat shield has to withstand temperatures exceeding 2,000 degrees Celsius. Any failure means the crew burns up in the atmosphere. And after all that, after surviving everything Mars and space threw at them, the crew would land on Earth significantly weakened. They'd need immediate medical attention, months of rehabilitation to rebuild muscle and bone, psychological counseling to readjust to life on Earth. Some astronauts who've spent long periods in space report that gravity feels crushing when they first return. Everything is heavy, standing is exhausting. Even lifting your arms is difficult. Now, let's step back and think about what all of this means. We've talked about propulsion systems, launch windows, ISRU, radiation, dust psychology, medical emergencies, and re-entry. Every single one of these is a hard problem. Not impossible, but hard. Each one requires technology that either doesn't exist yet or hasn't been tested at the scale needed for a Mars mission. And here's the kicker. They all have to work together, perfectly. For years, a Mars return mission is what engineers call a tightly coupled system. Every subsystem depends on every other subsystem. The power system has to provide enough energy for life support, ISRU, communications, and science operations. The ISRU system has to produce enough propellant for the return launch. The habitat has to protect the crew from radiation and maintain a livable environment for 18 months. The propulsion system has to function flawlessly for launch, orbital insertion, and Earth return. If any single critical system fails, the entire mission could be lost. This is fundamentally different from space missions we've done before. The Apollo program was risky, certainly, but it was short. The crew was only gone for about a week. They brought everything they needed from Earth. If something went wrong, they could abort and come home within days. The International Space Station is long duration, but it's in low Earth orbit. We can send supplies every few months. We can evacuate the crew in hours if necessary. Mars is neither short duration nor easily accessible. It's a multi-year commitment in a location 8 months away from any help. The systems need to have redundancy and reliability far beyond anything we've built before, and that takes time and money to develop, lots of both. This is why realistic timelines for human Mars missions keep slipping. Not because engineers don't know what to do, but because doing it requires technology that doesn't exist yet and political will to fund development over decades. Some space enthusiasts get frustrated with these cautious assessments. They point to past achievements like Apollo and say we just need to commit to accept risk the way we did in the 1960s. But Apollo was a sprint, a focused, massively funded, time-limited program with clear goals and presidential backing, and we lost 3 astronauts in the Apollo 1 fire before we even left the ground. 2 more came within hours of dying when Apollo 13's oxygen tank exploded. We were extraordinarily lucky that we didn't lose more crews during the moon missions. A Mars program can't be a sprint. It's a marathon. Actually, it's more like an ultramarathon. You need sustained funding for decades. You need international cooperation because no single nation can realistically afford to do it alone. You need technological breakthroughs in multiple fields simultaneously. And you need public and political support to continue through setbacks. Because there will be setbacks. There might even be loss of life. Space exploration is dangerous. We've always known that. But the dangers of Mars are an order of magnitude greater than anything we've attempted before. So is a return trip from Mars actually possible? Yes, the physics allows it. We're not talking about faster-than-light travel or violating thermodynamics. Everything required to send humans to Mars and bring them back exists within the boundaries of known science and engineering. But possible doesn't mean easy, and it doesn't mean soon. The technology readiness level for critical systems is still too low. The costs are astronomical, the risks are enormous, and the timeline is measured in decades, not years. Let's talk about mission architectures, because there are actually several different approaches to getting humans to Mars and back. Each one has trade-offs. Each one makes different assumptions about technology, risk tolerance, and cost. And understanding these different approaches helps explain why there's so much debate in the aerospace community about the best path forward. The first major architecture is what NASA calls the Moon to Mars approach. The idea is you don't go straight to Mars. Instead, you use the Moon as a proving ground. You develop and test technologies in lunar orbit and on the lunar surface, where help from Earth is only days away, not months. You build the Gateway Lunar Outpost. You practice living off the land with lunar ISRU. You test habitats, rovers, power systems, and life support in an environment that's hostile but not as distant as Mars. This is the approach NASA has been officially pursuing since the Artemis program was established. Artemis is supposed to return humans to the Moon by the mid-2020s, establish a sustained presence, and use that as the foundation for eventual Mars missions sometime in the late 2030s or 2040s. The advantage is that you reduce risk by testing everything incrementally. The disadvantage is that it takes longer and costs more upfront. Critics argue that the Moon is so different from Mars that you're not really preparing for the unique challenges of the red planet. You're just doing Moon missions and calling it Mars preparation. There's also the question of whether Gateway makes sense as architecture. Gateway is a small space station in lunar orbit designed to serve as a staging point for lunar surface operations. But it's in a highly elliptical orbit that takes a week to complete one loop around the Moon. From an engineering standpoint, some experts question whether Gateway provides enough value to justify its cost and complexity. It's not on the lunar surface, where you could practice ISRU. It's not in low Earth orbit, where it's easy to access. It's in this middle ground that might be politically appealing because it involves international partners, but operationally it's unclear how much it actually advances Mars readiness. Then there's the Mars Direct approach, Popularized by aerospace engineer Robert Zubrin, Mars Direct is the opposite philosophy. Go to Mars as quickly and cheaply as possible with minimal infrastructure. Zubrin's concept, first proposed in the early 1990s, involves sending an Earth return vehicle to Mars first, carrying a small nuclear reactor and ISRU equipment. The ERV lands on Mars and spends about 18 months manufacturing propellant for the return trip. Once the propellant tanks are full, you send the crew in a separate habitat module. They land near the ERV, do their exploration, and when it's time to leave, they use the pre-positioned return vehicle. The beauty of Mars Direct is its simplicity. You're not building giant space stations or staging in lunar orbit. You're not developing elaborate reusable spacecraft. You use existing heavy-lift rockets, relatively simple mission plans, and aggressive use of ISRU to minimize the mass you have to launch from Earth. Zubrin estimated in the 1990s that the entire program could be done for around $30 to $50 billion spread over a decade. Adjusted for inflation and modern cost estimates, that's probably more like 100 to 150 billion today, which is still dramatically cheaper than some NASA estimates for Moon to Mars. But Mars Direct makes a lot of assumptions. It assumes ISRU works reliably on the first try. It assumes you can land heavy payloads accurately on Mars. It assumes nothing critical breaks during the 18 months the ERV is sitting on the surface before the crew arrives. If the ISRU system fails, or if a dust storm damages the solar panels, or if any of 100 other things go wrong, the crew arrives with no way home. That's a level of risk that NASA, with its extremely conservative safety culture developed after the Challenger and Columbia disasters, is unwilling to accept. SpaceX's Starship architecture is philosophically closer to Mars Direct than to NASA's Moon to Mars. Elon Musk has talked about sending dozens of starships to Mars during a single launch window, creating a convoy of cargo and crew vehicles. The cargo ships would land first, carrying supplies, equipment, and ISRU systems. The crew ships would follow once infrastructure is in place. Starship is designed to be fully reusable, which theoretically drives down costs. If you can reuse the same vehicle multiple times, you're only paying for propellant and operations rather than building a new spacecraft for every mission. But Starship still exists, mostly on paper, for Mars purposes. The vehicle is being tested for Earth orbit operations and lunar missions under NASA's Artemis program. Orbital refueling, which is critical to the Mars architecture, hasn't been demonstrated yet. Landing a 100-ton spacecraft on Mars is an unsolved problem. SpaceX's Raptor engines have flown, but the integrated lander configuration hasn't been tested in Martian atmospheric conditions, and the timelines keep slipping. Musk originally talked about humans on Mars by the mid-2020s, then the late 2020s. Now SpaceX is prioritizing lunar missions, which pushes Mars further into the 2030s. There's also a hybrid approach that some mission planners advocate. Send cargo missions to Mars first using slow, efficient electric propulsion over multiple years to pre-position supplies and equipment. Then send the crew on a fast trajectory using nuclear thermal propulsion to minimize their time in deep space and reduce radiation exposure. This combines the efficiency of electric propulsion for cargo with the speed advantages of nuclear propulsion for crew, but it requires developing both technologies and coordinating missions across multiple launch windows, which adds complexity. Another concept that gets discussed is the split mission architecture, where you launch different components separately and assemble them in Earth orbit or at a Lagrange point before heading to Mars. You might launch the habitat module on one rocket, the propulsion stage on another, and the crew on a third. They dock together in space, then fire the engines for Mars. The advantage is you're not constrained by the payload capacity of a single launch vehicle. You can build a much larger, more capable spacecraft. The disadvantage is that orbital assembly and refueling are complicated. expensive, and add points of potential failure. All of these architectures share common elements. They all need life support systems that can recycle air and water with near-perfect efficiency for years. They all need radiation shielding, or at least a storm shelter where the crew can hide during solar particle events. They all need reliable power generation on Mars. They all need some form of ISRU to make propellant, or at least water and oxygen. And they all need propulsion systems capable of landing on and launching from Mars. Now here's where things get interesting. Some engineers and scientists are starting to ask a fundamental question. Do we actually need to send humans to Mars at all? Could we accomplish the scientific objectives with robots instead? Because robots don't need life support, they don't need food or water, they don't get bored or lonely, they don't require return propulsion because they can stay on Mars indefinitely. And if a robot mission fails, nobody dies. The counter-argument is that humans are far more capable than robots. A geologist on Mars could cover more ground in a day than a rover could in weeks. Humans can make judgment calls, adapt to unexpected situations, and perform complex tasks that would take months to program into a robot. The Apollo astronauts collected more scientifically valuable samples in a few days on the Moon than all the robotic missions combined. There's no substitute for human intuition, flexibility, and problem-solving ability. But robotics and artificial intelligence are improving rapidly. The Perseverance rover has a degree of autonomy that earlier rovers didn't. It can navigate obstacles, select scientific targets, and make decisions without waiting for commands from Earth. Future robots could be even more capable. Imagine a swarm of semi-autonomous robots working together on Mars, coordinated by AI systems, with occasional high-level guidance from scientists on Earth. They could explore vast areas, collect samples, even build infrastructure in preparation for eventual human arrival. There's a middle ground emerging in the space community. Send robots first to do the heavy lifting, then send humans for the high-value tasks that truly require human presence. Use robots to prospect for water ice, to build landing pads, to set up power systems and ISRU plants. By the time humans arrive, the infrastructure is already in place and tested. The robots have done the dangerous groundwork. The humans can focus on exploration and science rather than survival. This is actually similar to how Antarctic research works. Before scientists arrive at a remote field site, logistics teams fly in supplies, set up tents and equipment, cache fuel. When the scientists arrive, they can focus on their research instead of spending all their time fighting the environment. Mars could work the same way, except the logistics team is robotic. Artificial intelligence is becoming central to this vision. Modern AI systems can analyze images faster than humans, identify geological features, even predict where to find scientifically interesting samples. Machine learning algorithms are already being used to process data from Mars orbiters and rovers. Future AI systems could manage entire missions autonomously, making real-time decisions without the 20-minute communication delay. They could troubleshoot problems, optimize resource usage, and adapt mission plans based on what they discover. But AI also introduces new challenges. How do you ensure an autonomous system makes safe decisions? What happens if the AI makes a mistake that endangers the mission? How much authority should we give to machines when human lives might depend on their choices? These aren't just technical questions, they're ethical and philosophical. We're venturing into territory where humans might be supervising machines that are essentially running the show. There's also the question of mission purpose. Why are we going to Mars? If the goal is purely scientific, to understand the geology and search for past life, then robotic missions might be sufficient and far more cost-effective. A single human Mars mission might cost hundreds of billions of dollars. For that same amount, you could send dozens of robotic missions to Mars, Venus, the moons of Jupiter and Saturn. You could build bigger telescopes, You could fund research that might have more immediate benefits for humanity. But if the goal is to establish humanity as a multi-planetary species, to create a backup for civilization in case something catastrophic happens to Earth, then you need humans on Mars, permanently. Not just visiting, but living there, building habitats, raising families, creating a self-sustaining colony. That's a completely different mission with completely different requirements. And it's a project that would span not decades but centuries. This is where the conversations splits between pragmatists and visionaries. The pragmatists look at the enormous technical challenges, the staggering costs, the risks, and they say we need to go slow, be cautious, develop technology incrementally. The visionaries look at the same challenges and say we need to move fast, accept risk, and commit to the goal because the long-term survival of humanity depends on it. Both perspectives have merit, and the tension between them shapes policy and funding decisions. Elon Musk is clearly in the visionary camp. He's talked about building a city of 1 million people on Mars. That's not a scientific outpost. That's colonization on a massive scale. It would require thousands of flights, millions of tons of cargo, infrastructure that makes current plans look trivial, and it assumes that all the technical problems can be solved, that ISRU can be scaled up enormously, that people will actually want to live on a frozen, irradiated desert planet millions of kilometers from home. Some scientists are skeptical. They point out that Mars is a terrible place for humans. Even with advanced technology, life on Mars would be harsh, dangerous, and constrained. You'd spend your entire life in pressurized habitats or spacesuits. You'd never feel wind on your face or swim in an ocean. Your children would grow up in 1/3 gravity, which might cause irreversible physiological changes. They might never be able to visit Earth because their bodies couldn't adapt to full gravity. Is that really the future we want? Others argue that difficulty doesn't make something unworthy. Humanity has always pushed into difficult environments. Antarctica is hostile, yet we maintain research stations there. The deep ocean is crushing and dark, yet we've explored it. Space is the ultimate frontier, and Mars is the most accessible stepping stone. If we wait until it's easy, we'll never go. And if we never go, we'll never know what we might have discovered or become. There's also a philosophical dimension to this. Human space exploration is about more than science or survival. It's about aspiration, about reaching beyond our current limits, about the human drive to explore and expand. The Apollo missions inspired a generation. They demonstrated what humanity could achieve when we set ambitious goals. Mars could do the same. It could reignite interest in science and engineering, inspire young people to pursue careers in technical fields, and unite nations around a common purpose. But inspiration doesn't pay the bills. Governments allocate limited budgets, and space exploration competes with healthcare, education, infrastructure, and defense. When NASA's Mars Sample Return program was projected to cost $11 billion, Congress looked at that price tag and said no. That money could fund a lot of other priorities. The case for Mars has to be compelling enough to justify the expense, and right now, it's not clear that it is. This is where private spaceflight becomes crucial. If companies like SpaceX can dramatically reduce launch costs through reusability, if they can develop capabilities without depending entirely on government funding, then Mars missions become more feasible. But private companies need a business model. SpaceX makes money launching satellites and flying crew to the ISS. What's the business model for Mars? Tourism? Mining? There's no obvious revenue stream that would justify the investment in the near term. Some have suggested that asteroid mining or lunar resource extraction could fund Mars exploration. If you could mine water ice from lunar craters or extract precious metals from asteroids, you could create an off-Earth economy that generates wealth to fund deeper exploration. But asteroid mining is still speculative. No one has successfully demonstrated the technology. And even if it works, it could be decades before it's profitable enough to fund Mars missions. So we're left with a chicken and egg problem. We need economic activity in space to fund Mars exploration, but we need infrastructure and technology development to enable that economic activity. And developing that infrastructure requires upfront investment that doesn't have an immediate return. Governments could provide that initial investment, but they need political will, and political will requires public support, which requires inspiration and a clear vision. All right, let's say we actually pull it off. Let's say all the technology works, the funding materializes, and we successfully land humans on Mars. They spend 18 months exploring, collecting samples, doing science. Then they climb into their ascent vehicle, launch into Mars orbit, rendezvous with the return spacecraft, and head back to Earth. 6 months later, they're approaching Earth at 11 kilometers per second, heat shield glowing white hot, parachutes deploying, and they splash down in the Pacific Ocean. Helicopters swoop in. Recovery crews pull them from the capsule. The astronauts are weak, exhausted, but alive. They're heroes. They've done what no human has ever done before. And then we immediately quarantine them. For weeks, maybe months. Because we have absolutely no idea what they might be bringing back with them. This is the problem of planetary protection, and it's one of the most serious and underappreciated challenges of Mars sample return. The concern works in both directions. First, we don't want to contaminate Mars with Earth life. That's called forward contamination. But equally important, we don't want to contaminate Earth with potential Martian life. That's backward contamination. And the protocols for handling this are, to put it mildly, inadequate. Let's start with forward contamination. Every spacecraft we've sent to Mars carries Earth microbes. We try to sterilize them, but it's impossible to eliminate all life. Bacteria can survive in the most extreme environments. They've been found in the upper atmosphere, in deep-sea hydrothermal vents, inside nuclear reactors, in the vacuum of space. Some microbes form spores that can survive intense heat, radiation, and desiccation for years. When we send a rover to Mars, we bake it in ovens, swab it with alcohol, use UV light and chemical treatments. But studies have shown that some microbes still survive. NASA and the Committee on Space Research, which is the international body that sets planetary protection standards, classify missions based on their potential to contaminate other worlds. Mars rovers are Category V missions, which means they're going to a place where life might exist. So they require strict sterilization procedures. But even with all precautions, we know Earth microbes have reached Mars. The question is whether they can survive and reproduce once they're there. The Martian environment is incredibly hostile to life as we know it. The thin atmosphere, intense UV radiation, extreme cold, and lack of liquid water make it difficult for Earth organisms to survive, but difficult isn't impossible. In 2020, scientists reported that certain microbes exposed to simulated Martian conditions could survive for extended periods, especially if they were shielded underground or inside rocks. If humans land on Mars, the contamination risk increases exponentially. A human crew brings about 37 trillion microbes with them just in their bodies. Gut bacteria, skin bacteria, bacteria in their mouth and respiratory system. Every time they use an airlock, every time they handle equipment, every time they produce waste, they're potentially releasing Earth microbes into the Martian environment. Even with the most rigorous containment protocols, some contamination is inevitable, and if those microbes find their way into a hospitable microenvironment, perhaps underground, where there's ice or even liquid water, they could potentially survive and spread. Why does this matter? Because if we're trying to search for indigenous Martian life, contamination from Earth makes that search nearly impossible. How do you distinguish between a microbe that evolved on Mars and one that hitched a ride from Earth? You can sequence its DNA, But if Earth microbes have been living on Mars for years, evolving and adapting, they might look different enough to cause confusion. And if Earth life outcompetes and displaces any native Martian life, we might destroy the very thing we went to Mars to find. This isn't just a hypothetical concern. There's strong evidence that liquid water exists underground on Mars. Radar observations from orbit have detected what appear to be subglacial lakes beneath the Martian South Polar ice cap. If there's liquid water, there could be life. And if we accidentally introduce Earth microbes into those environments before we've had a chance to study them in their pristine state, we could be committing an act of biological vandalism on a planetary scale. Then there's backward contamination, which is potentially even more serious. What if Mars has life? Not just fossilized evidence of past life, but actual living organisms. And what if we bring them back to Earth? This is the scenario that keeps planetary protection officers awake at night, because we have no idea how Martian life would interact with Earth's biosphere. The worst-case scenario goes something like this. Martian microbes, having evolved completely independently from Earth life, have biochemistry we don't understand. They're brought back in a sample return capsule. During landing or recovery, there's a breach. The microbes are released into Earth's environment. Our immune systems have never encountered anything like them, so we have no defense. They spread rapidly, causing disease we can't treat because nothing in our medical arsenal works against alien biochemistry. It's the plot of every pandemic thriller you've ever watched, except the pathogen is from another planet. Now, most scientists think this scenario is extremely unlikely. For Martian life to be dangerous to humans, it would need to be compatible enough with our biochemistry to interact with our cells, but different enough that our immune systems can't recognize it. That's a very narrow window. Most likely, if Martian life exists, it would be so different from Earth life that it simply couldn't infect us. It would be like trying to catch a computer virus by eating your laptop. The systems are incompatible. But we don't know. We've never encountered extraterrestrial life. We don't know what's possible. And the potential consequences of being wrong are catastrophic. So the international scientific community has established that any samples returned from Mars must be contained absolutely until they've been proven safe. Not probably safe, not almost certainly safe, absolutely safe. This is where things get complicated, because what does absolute containment mean for a Mars sample return? You need a facility that can handle potentially hazardous biological material with perfect isolation from the environment. No leaks, no breaches, no contamination in or out. The samples need to be studied in this facility for months or years before anyone can be certain they don't contain dangerous organisms, and even then, proving a negative is almost impossible. How long do you study samples before you're confident there's nothing dangerous in them? NASA built a facility like this for the Apollo missions. The Lunar Receiving Laboratory in Houston was designed to quarantine moon rocks and astronauts until scientists could confirm the moon was sterile. The Apollo 11, 12, and 14 crews spent weeks in quarantine. The moon rocks were handled in sealed chambers by technicians using gloves built into the walls. But the facility was dismantled decades ago, and we'd need something far more sophisticated for Mars samples. Current estimates suggest a Mars sample receiving facility would cost at least $500 million to build and require years of planning and construction. Europe is actually ahead of the United States on this. The European Space Agency has been developing plans for a Mars sample return handling facility. They've conducted studies on what level of biocontainment would be required, how samples would be transferred and analyzed, what protocols would govern the research. But the facility doesn't exist yet. And without it, you can't safely return samples to Earth. This is one reason why China's Tianwen-3 mission is so interesting from a planetary protection standpoint. If China brings back samples by 2031, they'll need their own sample containment facility. They'll need to convince the international scientific community that their protocols are adequate. And they'll set the precedent for how Mars samples are handled. Whatever standards they implement will influence future missions. There's also the legal dimension. Who owns samples from Mars? Who has jurisdiction over a Mars sample return facility? If a containment breach occurs, who's liable? International space law is based on the Outer Space Treaty of 1967, which establishes that celestial bodies are the province of all mankind. No nation can claim sovereignty over the Moon or Mars, but the treaty is vague on ownership of samples. If a country or company retrieves material from Mars, do they own it? Can they sell it? Can they refuse to share it with the international scientific community? The Outer Space Treaty also requires that space exploration be conducted to avoid harmful contamination and adverse changes to Earth's environment. That's the legal basis for planetary protection protocols, but the treaty was written in the 1960s when Mars sample return was pure science fiction. The legal framework hasn't been updated to address modern challenges. There's no international body with enforcement authority. There's no clear mechanism for ensuring compliance. It's mostly voluntary standards and peer pressure. This could become a serious issue if private companies get involved in Mars exploration. SpaceX has stated that their goal is to establish a self-sustaining city on Mars. But they're a private company, not a signatory to international treaties. If SpaceX lands cargo on Mars, are they required to follow NASA's planetary protection protocols? What if their contamination standards are less rigorous? What if they bring material back from Mars without going through proper containment procedures? These aren't hypothetical questions. They're practical challenges that need answers before we start sending multiple missions to Mars, and the answers require international cooperation, which is notoriously difficult to achieve. Different countries have different interests. Different scientific communities have different priorities. Getting everyone to agree on standards and enforcement mechanisms takes years of negotiation. Then there's the question of indigenous rights, which might sound absurd when we're talking about a planet that's likely lifeless. But let's say we do find life on Mars. Even if it's just microbes in subsurface ice, that's an independent origin of life, possibly the only other example in the universe that we know of. Does it have any rights? Do we have an ethical obligation to protect it? Or can we terraform Mars and wipe out native life in the process? Some philosophers and ethicists argue that life, any life, has intrinsic value independent of its utility to humans. If Martian life exists, we should preserve it, study it, but not destroy it. Others argue that human interests take precedence, that if we need to transform Mars to ensure the survival of humanity, that's morally justified even if it means displacing native microbes. It's a debate with no easy answers, and it's one we need to have before we're confronted with the actual choice. There's also the issue of informed consent from the Martian life, which obviously can't give consent because it's microbes or at best very simple organisms. But the principle raises an important point. We're making decisions that affect another world and potentially another biosphere without any input from that world's inhabitants, however primitive they might be. It's colonialism on a cosmic scale, and it brings up uncomfortable parallels with how humans have historically treated indigenous populations and ecosystems on Earth. These ethical considerations extend to future human colonization. If we establish a permanent human presence on Mars, how do we govern it? Does Mars become subject to Earth laws? Which Earth laws? If people are born on Mars, are they citizens of Earth nations or of Mars itself? If Mars develops its own society and culture, does it have the right to self-determination? We're talking about questions that won't become relevant for decades or centuries, but the decisions we make now about how we approach Mars exploration will shape the answers. There's a school of thought in the space community called space environmentalism. The core idea is that space, including other planets, has value beyond what it can provide to humans. Just as we've developed environmental ethics on Earth that recognize the intrinsic value of wilderness and ecosystems, we should extend those ethics to space. Mars shouldn't be seen merely as a resource to exploit or a destination to conquer, but as a world deserving of respect and careful stewardship. This perspective conflicts with the more expansionist view that sees Mars as humanity's manifest destiny, a new frontier to settle and transform. The tension between these viewpoints is real and growing. As Mars missions transition from purely scientific endeavors to potential colonization efforts, these debates will intensify. And they're not just abstract philosophy. They influence policy, funding decisions, and mission design. For example, if we take space environmentalism seriously, we might decide that certain regions of Mars should be designated as protected areas, off-limits to human activity, to preserve them in their natural state for scientific study. The areas with subsurface water would be prime candidates. But if we're trying to establish a colony, those same regions are exactly where we'd want to go, because that's where the resources are. Water for drinking, for growing food, for making propellant. You can't build a self-sustaining colony in a desert with no accessible water. So we have competing interests, scientific preservation versus human settlement, and no clear framework for resolving them. The scientific community generally favors caution and protection. The commercial spaceflight sector favors expansion and development. Governments are caught in the middle, trying to balance scientific goals, economic interests, international cooperation, and national prestige. All of this assumes, of course, that we can actually get to Mars and back in the first place. Which brings us back to the fundamental challenges we've been discussing. The technology, the cost, the risk. Because even if we solve all the ethical and legal questions, even if we build perfect sample containment facilities and establish comprehensive planetary protection protocols, none of it matters if we can't physically transport humans to Mars and return them safely to Earth. And here's the uncomfortable truth that doesn't get talked about enough. We're probably decades away from having the capability to do that reliably. Not because the physics is impossible, but because the engineering is hard and the political will is lacking. NASA's official timelines talk about humans on Mars in the 2030s or 2040s. But those timelines have been slipping for years, and without sustained funding and commitment, they'll keep slipping. China might change the equation. If Tianwen-3 succeeds in returning samples by 2031, it could create the political pressure needed to accelerate Western efforts. The space race dynamic that drove Apollo could repeat itself, but it's not guaranteed. Public interest in space is lower now than it was during the Cold War. The threat perception is different, and the costs are higher. So we're left with this strange situation where going to Mars is technically possible, probably necessary for humanity's long-term future, and extraordinarily difficult to actually accomplish. It's the sort of challenge that requires thinking on timescales longer than election cycles or quarterly earnings reports. It requires international cooperation on a scale we've rarely achieved. And it requires accepting that some of the people who start this project won't live to see it completed. Let's get practical. Enough abstract discussion about ethics and timelines. What technologies are actually being developed right now that could make a Mars return mission possible? What's moving from the laboratory to flight hardware? And what are the key problems that still don't have solutions? Because this is where the rubber meets the road. This is where ambitious plans either become reality or remain PowerPoint presentations. Start with propulsion. We've talked about chemical rockets and nuclear thermal propulsion conceptually, but what's actually being built? NASA's Space Launch System is real. It flew for the first time in 2022 with the Artemis I mission. SLS is a heavy-lift rocket capable of putting about 95 metric tons into low Earth orbit in its initial configuration, with planned upgrades that could increase that to 130 metric tons. That's Apollo-era lifting capacity. The rocket exists, it works, but here's the problem. SLS costs about $4 billion per launch. $4 billion. For a single flight, you can't build a sustainable Mars program with $4 billion launches. At that price, every mission becomes a national event requiring years of planning and political justification. For comparison, SpaceX's Falcon Heavy, which is currently operational, costs about $150 million per launch and can put about 63 metric tons into low Earth orbit. That's already a 25-fold cost reduction. And Starship, when fully operational, is projected to cost even less per launch because it's fully reusable. Reusability is the key to reducing costs. Traditional rockets are expendable. You use them once and throw them away. It's like building a brand new 747 for every flight and then crashing it into the ocean. Economically insane, but that's how spaceflight has worked for 60 years. SpaceX demonstrated that you can land and reuse rocket boosters with Falcon 9. They've now reflown individual boosters more than 20 times. That's proven technology. Starship takes the concept further by making both the booster and the upper stage reusable. But here's what doesn't exist yet: orbital refueling. Starship's Mars architecture depends on launching a ship to orbit, then sending up multiple tanker flights to refuel it before it heads to Mars. You might need 10 to 15 refueling flights for a single Mars mission. That's a lot of orbital rendezvous and docking, which is routine for the ISS, but has never been done for cryogenic propellant transfer at the scale required. Liquid methane and liquid oxygen need to be kept extremely cold. You have to manage boil-off. You have to transfer thousands of tons of propellant in zero gravity, where fluids behave in non-intuitive ways. NASA awarded SpaceX a contract to demonstrate orbital refueling as part of the Artemis program, because a moon-capable Starship also requires refueling in orbit. SpaceX is supposed to demonstrate this technology by the mid-2020s. If they succeed, it's a game-changer for Mars. If they don't, the entire Starship Mars architecture falls apart. This is a critical path technology that doesn't have a backup plan. Nuclear thermal propulsion is in a different stage of development. NASA has been working on NTP concepts for decades, but nothing has flown. In 2023, NASA partnered with DARPA on the Draco program, which aims to demonstrate a nuclear thermal rocket in space by 2027. That timeline is ambitious, possibly unrealistic, but at least there's active development and funding. The challenges are significant. You're building a nuclear reactor that has to operate reliably in the extreme environment of space, providing thrust for hours during orbital burns. The fuel elements have to withstand temperatures above 2,500 Celsius, while a hydrogen propellant flows through them at high pressure. There are also political challenges. Launching nuclear material into space makes people nervous. The reactor wouldn't be activated until the spacecraft is already in orbit, so launch accidents wouldn't spread radioactive material. But that requires public education and confidence in the safety systems. And you need international agreements, because a nuclear-powered spacecraft isn't just a national project. It affects space policy globally. Electric propulsion is further along in development. Hall-effect thrusters and ion engines are already used on satellites for station keeping and orbit raising. NASA's Dawn mission used ion propulsion to visit the asteroids Vesta and Ceres, but scaling up electric propulsion to move heavy cargo to Mars requires more powerful systems. NASA has been developing the Advanced Electric Propulsion System, which uses xenon or krypton propellant and can produce thrust for years using solar or nuclear electric power. The technology is mature enough that it could be used for cargo missions within the next decade. Now let's talk about life support, because keeping humans alive for 3 years is arguably harder than getting them to Mars in the first place. The ISS has sophisticated life support systems that recycle water and oxygen, but they're not closed loop. The ISS receives regular resupply missions carrying water, food, spare parts, and other consumables. A Mars crew can't rely on resupply. They need systems with much higher recycling efficiency. Water recycling on the ISS currently recovers about 93 to 94% of water from urine, sweat, and humidity in the air. That's impressive, but the remaining 6 to 7% is lost and has to be replaced. Over a 3-year Mars mission, those losses add up. You'd need to bring tons of extra water just to compensate for inefficiency. NASA is working on next-generation systems that can achieve 98% recovery or higher. The technology involves better membranes, more efficient filters, and processes like forward osmosis and supercritical water oxidation that can break down organic compounds more completely. Oxygen is recycled on the ISS through electrolysis, splitting water molecules into hydrogen and oxygen. The oxygen is returned to the cabin atmosphere. The hydrogen is usually vented overboard, which represents a loss. For Mars, you'd want to recapture that hydrogen and combine it with carbon dioxide from the cabin atmosphere to produce water and methane through the Sabatier reaction. That closes the loop. NASA has tested these systems on the ISS, and they work. But making them reliable enough for a multi-year mission without maintenance from Earth is another challenge. Then there's food. Current space food is pre-packaged and designed for shelf life, but 3 years is a long time, and psychological research shows that food variety and quality are important for crew morale. NASA has been researching in space food production, primarily growing plants. Fresh vegetables would provide nutrition, psychological benefits, and contribute to air revitalization by consuming carbon dioxide and producing oxygen. The veggie and advanced plant habitat experiments on the ISS have successfully grown lettuce, radishes, peppers, and other crops in microgravity. But growing food on Mars introduces new challenges. Martian gravity is about 38% of Earth's, which is enough for water and nutrients to behave more normally than in microgravity. But we don't fully understand how plants grow in partial gravity. Does it affect root development, nutrient uptake, growth rates? We won't know until we try. Soil is another issue. Martian regolith contains perchlorates, which are toxic. You can't just fill a planter with Martian dirt and start growing tomatoes. The soil would need to be washed or treated to remove perchlorates, then enriched with organic matter and nutrients. Some researchers have been experimenting with Mars regolith simulants, mixing them with compost and testing whether Earth plants can grow. Results have been mixed. Some plants tolerate it, others struggle. Developing reliable agricultural systems for Mars is a long-term research project. Radiation shielding is one area where we still don't have great solutions. We've talked about the problem, but what are the actual countermeasures being developed? Water shielding is one approach. Water is an effective radiation absorber, and you need to carry water anyway for drinking and life support. Some habitat designs incorporate water tanks in the walls, so the water serves double duty as both resource and shielding. The challenge is mass. Surrounding a habitat with enough water to provide significant radiation protection adds tons of weight. Regolith shielding is more practical once you're on Mars. Pile Martian dirt over your habitat and you get excellent protection. Several habitat concepts use inflatable structures that are deployed on the surface, then covered with 1 meter or more of regolith. The dirt provides radiation shielding, thermal insulation, and protection from micrometeorites. Rovers or robotic systems would do the excavation and piling, but this doesn't help during the 6-month flights to and from Mars, where you're exposed to deep space radiation with no planet to shield you. One intriguing possibility is electromagnetic shielding. Instead of using mass to absorb radiation, you use magnetic fields to deflect it, similar to how Earth's magnetic field protects us. Several research groups have explored this concept. You generate a magnetic field around the spacecraft using superconducting magnets. Charged particles, which make up solar wind and most cosmic rays, would be deflected by the field. The problem is that the magnetic fields need to be very strong and cover a large volume, which requires heavy magnets and significant electrical power. Current designs suggest this might work for solar particle events, but wouldn't provide complete protection against galactic cosmic rays. Pharmaceutical countermeasures are another area of research. What if you could take a drug that helps your cells repair radiation damage more efficiently, or that stimulates production of immune cells to replace those killed by radiation? Several compounds are being studied, including antioxidants that reduce oxidative stress from radiation, and genetic therapies that might upregulate DNA repair mechanisms. None of these are ready for Mars missions yet, but they're active areas of research. The challenge is that radiation damage is cumulative and affects multiple body systems. There's no single drug that can fix everything. For ISRU, the technology exists in laboratories, but hasn't been demonstrated at operational scale on Mars. The MOXIE experiment on the Perseverance rover is producing oxygen from Martian carbon dioxide right now. It's the size of a car battery and produces about 6 to 10 grams of oxygen per hour. That's a proof of concept. For a human mission, you'd need a system thousands of times larger, producing kilograms of oxygen per hour, operating reliably for years with minimal maintenance. Extracting water from Martian ice is another challenge. We know ice exists near the surface at high latitudes, but getting to it requires drilling or excavating. The ice is mixed with soil, so you need to separate it. One approach is to heat the regolith and capture the water vapor as it sublimates. Another is to extract chunks of ice-rich material and process it in a thermal extraction unit. SpaceX has talked about using solar concentrators, essentially giant mirrors that focus sunlight to provide heat for ice extraction. But this hasn't been tested on Mars. Making methane fuel from carbon dioxide and water is chemistry that works on Earth. The Sabatier reaction is well understood. Combining hydrogen and carbon dioxide at the right temperature and pressure with a catalyst produces methane and water. You electrolyze water to get hydrogen and oxygen, then use the hydrogen for the Sabatier reaction. The entire process can be powered by solar panels or a nuclear reactor. The engineering challenge is building systems that are reliable, automated, and can operate in Martian conditions. Dust contamination, thermal cycling, equipment wear. These are all problems that need solutions. Landing large payloads on Mars is a major technological gap. The heaviest thing we've successfully landed on Mars is the Perseverance rover at about 1 metric ton. A human mission would require landing vehicles weighing 10 to 20 tons or more. Earth's thick atmosphere allows parachutes and airbags to work for landing. Mars's thin atmosphere doesn't provide enough drag for parachutes to slow heavy vehicles sufficiently. You need powered descent, firing rockets to slow down and land gently. NASA has been developing supersonic retropropulsion, where you fire retro rockets while still traveling at supersonic speeds through the atmosphere. This is counterintuitive because the rocket exhaust interacts with the supersonic airflow in complex ways. But it works. SpaceX's Falcon 9 boosters use supersonic retropropulsion to land back on Earth. For Mars, you need larger engines and more fuel because the landing velocities are higher and you have to carry everything with you. SpaceX is designing Starship to land vertically on Mars using its Raptor engines, but landing a 100-ton spacecraft on Mars has never been attempted. The first few tries will be risky, China is developing its own Mars landing technology. Their Tianwen-1 mission successfully landed a rover in 2021, demonstrating entry, descent, and landing capability. For sample return, they'll need precision landing to put the ascent vehicle near areas where the rover has collected samples, and they'll need to launch from Mars, which no one has done before. The Mars Ascent vehicle being developed for sample return missions is essentially a small rocket that has to work flawlessly on its first try after sitting on Mars for months or years. It has to ignite reliably, launch into a precise orbit, and rendezvous with a spacecraft waiting in orbit to capture the sample container. Orbital rendezvous is routine in low Earth orbit. We do it every time a cargo ship docks with the ISS. But in Mars orbit, there's no mission control providing real-time guidance. The spacecraft have to do it autonomously using onboard sensors and computers. The sample canister will be in an elliptical orbit after launch from the surface. The orbiter has to match orbits, find the tiny canister in the vastness of space, approach it carefully, and capture it. Any failure in this sequence, and the samples are lost. For human missions, the orbital rendezvous is even more critical because lives depend on it. The crew launches from Mars in an ascent vehicle and has to dock with the Earth return spacecraft in orbit. If the rendezvous fails, they're stranded. There's no rescue. Some mission architectures include redundancy, like having 2 ascent vehicles or keeping the return spacecraft in a lower orbit to reduce the rendezvous challenge. But redundancy adds mass and cost. In space manufacturing is an emerging technology that could help with Mars missions. Instead of carrying all spare parts and tools from Earth, you manufacture them as needed using 3D printers. The ISS has had 3D printers for years, producing small plastic parts and tools. More advanced systems can print with metal, ceramics, and composites. For Mars, this could be transformative. You could print replacement parts for broken equipment. You could manufacture construction materials using Martian regolith as feedstock. You could even print entire structures. Several research groups are developing construction techniques for Mars using 3D printing. One approach is contour crafting, where a robot extrudes layers of material to build walls and structures. The material could be Martian concrete made from regolith, water, and binding agents. Another approach uses sintering, where you heat regolith with microwaves or lasers until it fuses into solid blocks or shapes. These technologies are being tested in Mars analog environments on Earth, like deserts and volcanic regions. But demonstrating them on Mars is years away. Artificial intelligence and robotics are advancing rapidly and will be crucial for Mars missions. Robots can prepare landing sites, build infrastructure, and assist astronauts with hazardous tasks. AI systems can monitor habitat systems, predict equipment failures, and optimize resource usage. The communication delay between Earth and Mars means astronauts can't rely on real-time support from mission control. They need AI systems that can provide guidance, troubleshoot problems, and even make decisions in emergencies. NASA is developing an AI assistant called Gateway, designed to support future deep space missions. It's like having an expert systems engineer and mission controller in a box. The AI can access all mission data, understand spacecraft systems, and help the crew solve problems. If something breaks, the AI can diagnose the issue, suggest repairs, and guide the crew through procedures. If an emergency happens, the AI can prioritize actions and allocate resources. This kind of technology is critical when you're 20 light minutes away from home and can't just call Houston for help. Medical AI is another area of development. IBM Watson and other medical AI systems are being adapted for space applications. The AI can analyze symptoms, suggest diagnoses, and recommend treatments based on the limited medical supplies available. It can guide a crew member through surgical procedures, if necessary, step by step. This doesn't replace a trained doctor, but it provides support when specialized expertise isn't available. Here's where things get interesting from an Earth applications perspective. Many of these technologies have immediate benefits here at home. Water recycling systems developed for space are being adapted for disaster relief and arid regions. 3D printing techniques are revolutionizing manufacturing. AI systems designed for spacecraft diagnostics are being used in hospitals and factories. The food production research is applicable to urban agriculture and sustainable farming. Radiation protection research informs cancer treatment and nuclear safety protocols. This is the hidden return on investment for space exploration. When you push the boundaries of technology to solve extreme challenges like living on Mars, you develop capabilities that have widespread applications. The Apollo program gave us advances in materials science, computer miniaturization, and telecommunications that shaped the modern world. Mars missions will drive innovation in automation, life support, energy systems, and advanced manufacturing that could transform life on Earth. Now we need to talk about what actually happens to the human body during a multi-year Mars mission, because this is where abstract engineering problems become viscerally real. You can have the best spacecraft, the most reliable propulsion, perfect life support systems, and still end up with a crew that's physically or psychologically incapable of completing the mission. The human body is not designed for space, it's not designed for Mars, and 3 years away from Earth does things to you that we're only beginning to understand. Start with the obvious one, microgravity. During the 6-month voyage to Mars, astronauts experience prolonged weightlessness. We know from ISS experience that this causes bone density loss at a rate of about 1 to 2% per month in weight-bearing bones. Over 6 months, that's 6 to 12% bone loss. Your skeleton literally dissolves into your bloodstream because your body decides it doesn't need to maintain bone strength when there's no gravity pulling on it. The calcium that leaches out of your bones ends up in your kidneys, increasing the risk of kidney stones, which would be a medical emergency on a spacecraft. Muscle atrophy is equally serious. Without gravity to work against, muscles weaken rapidly. Astronauts on the ISS exercise for 2 to 3 hours every day using resistance machines and treadmills to combat muscle loss. Even with aggressive exercise, they still lose muscle mass and strength. On a Mars mission, you'd need to maintain this exercise regimen for the entire journey. That's 2 to 3 hours of vigorous exercise every single day for 6 months, just to minimize the damage. And you're doing this in a cramped spacecraft where space is limited and privacy is non-existent. Cardiovascular deconditioning is another problem. In microgravity, your heart doesn't have to pump blood upward against gravity, so it becomes less efficient. Blood pressure regulation changes. When ISS astronauts return to Earth, many experience orthostatic intolerance, meaning they feel dizzy or faint when standing up because their cardiovascular system has adapted to weightlessness. Some astronauts have even fainted during landing. For a Mars mission, this is concerning because when you arrive at Mars and need to land the spacecraft, perform critical tasks, and deal with emergencies, you want the crew at full capability, not dizzy and weak. Vision problems are one of the most troubling discoveries from long-duration ISS missions. Many astronauts develop spaceflight-associated neuroocular syndrome, or SANS. Fluid shifts in microgravity cause increased pressure inside the skull, which can flatten the eyeball, cause the optic nerve to swell, and lead to permanent vision changes. Some astronauts who spent 6 months or more in space have come back with degraded vision that doesn't fully recover. For a Mars mission commander who needs to pilot a spacecraft during critical maneuvers, vision impairment could be mission-ending. The immune system is compromised in space. Studies of astronauts have shown that immune function is suppressed during spaceflight. White blood cell counts change. Immune responses to pathogens are weaker. Dormant viruses like herpes and chickenpox can reactivate because the immune system isn't keeping them in check. This is problematic because if someone gets sick on the way to Mars, the whole crew is exposed in the confined space, and their immune systems are all compromised. A respiratory infection that would be minor on Earth could become serious. Radiation exposure adds another layer of biological damage. We've discussed the radiation environment, but let's talk about what it actually does to cells. High-energy particles tear through DNA, breaking both strands and causing mutations. Most of the time, your cells can repair this damage, but sometimes the repairs are imperfect, leading to mutations that can cause cancer years or decades later. The estimated lifetime cancer risk for a 3-year Mars mission is somewhere between 5 and 20%, depending on solar activity, shielding, and individual susceptibility. That means 1 in 5 to 1 in 20 astronauts who go to Mars could develop cancer as a direct result of the radiation exposure, but cancer is a delayed effect. The immediate concern is acute radiation sickness from a large solar particle event. If astronauts are caught outside during a major solar storm, they could receive a radiation dose high enough to cause nausea, vomiting, fatigue, and immune system damage within hours. A very high dose could be lethal. This is why storm shelters are critical. The crew needs a protected area they can retreat to within minutes when solar activity is detected. Galactic cosmic rays are a different problem. These high-energy particles come from outside our solar system and can't be easily shielded. They pass through spacecraft walls, through water, through human tissue. When a cosmic ray particle passes through the brain, it leaves a trail of damage. Studies in mice exposed to simulated cosmic rays show that this damage can affect neurons and synapses, leading to cognitive impairment. The mice show memory problems, reduced learning ability, and increased anxiety. We don't know exactly how this translates to humans because we've never exposed humans to cosmic ray levels they'd experience on a Mars mission. But it's concerning. There's research suggesting that cosmic ray exposure could accelerate neurodegenerative diseases like Alzheimer's. The damage to brain tissue and the inflammatory response it triggers might increase the risk of dementia later in life. So astronauts who go to Mars might be accepting not just cancer risk, but the possibility of cognitive decline decades down the road. These are trade-offs that need to be clearly communicated and accepted. Now add the psychological challenges. 3 years in an isolated, confined environment with a small group of people is mentally grueling. Analogues on Earth, like Antarctic research stations and submarine deployments, give us some insight. People develop cabin fever, interpersonal conflicts escalate, and mental health issues emerge. Depression, anxiety, and sleep problems are common, and those are environments where you can at least communicate with home in real time and know that evacuation is possible if necessary. On a Mars mission, you're communicating with Earth with a 20-minute delay at best. You can't have a real conversation. You can't video call your family and interact naturally. Every message is asynchronous. You send something, wait, and get a response later. This delay creates psychological distance. You start to feel disconnected from Earth, from your support network, from everything familiar. And when problems arise, you can't get immediate advice or reassurance. Behavioral health research for long-duration missions focuses on crew selection, team dynamics, and coping strategies. NASA has been studying this for decades, but there's still a lot we don't understand. What personality traits predict success in isolated environments? How do you prevent conflicts from escalating when people can't just walk away? What activities and diversions help maintain mental health? How do you handle it if someone develops serious psychological problems that affect their ability to function? One insight from isolation studies is the importance of autonomy and control. People cope better when they feel they have some control over their environment and schedule. Micromanagement from mission control is counterproductive. The crew needs the authority to make decisions, adjust plans, and manage their own time. This conflicts with traditional mission control structures where every action is planned and monitored. For Mars, mission control will have to shift from directing to supporting. The crew is in charge. Earth provides advice and resources, but the crew makes the decisions. Another insight is the value of meaningful work. People who feel their work is important and contributes to something larger than themselves are more resilient. This is why crew selection for Mars will prioritize people who are intrinsically motivated by the mission, who find purpose in exploration and discovery. Going to Mars can't just be a job. It has to be something you deeply believe in, because that sense of purpose will sustain you through the hard times. Let's talk about countermeasures, because we're not helpless against these biological challenges. Pharmaceutical interventions are one approach. Bisphosphonates, which are drugs used to treat osteoporosis, can reduce bone loss in space. Astronauts on the ISS have taken these medications with some success. Other drugs can help with muscle retention, cardiovascular function, and immune system support. But all drugs have side effects, and taking multiple medications for years introduces risks. You're essentially chemically propping up body systems that evolution designed to work in Earth gravity. Exercise is the most proven countermeasure. The ISS has sophisticated exercise equipment, a treadmill, a stationary bike, and the Advanced Resistive Exercise Device, which provides up to 600 pounds of resistance for weightlifting exercises. These machines are essential for maintaining bone and muscle, but they're also large, heavy, and require regular maintenance. For a Mars spacecraft, you need similar equipment which takes up space and adds mass. Some mission designs include a rotating section that provides artificial gravity through centrifugal force, which would reduce or eliminate the need for exercise as a countermeasure. But rotating spacecraft introduce engineering complexity. Artificial gravity is actually the most comprehensive solution to microgravity health problems. If you spin the spacecraft to create centrifugal force, you can simulate gravity. The challenge is that spacecraft need to be large to do this comfortably. A small rotating craft would have high rotational rates and significant differences in gravitational force between your head and feet, which causes disorientation and nausea. To get 1 g of simulated gravity without making people sick, you need a rotation radius of at least 50 to 100 meters. That means a very large spacecraft or a tethered system where the crew habitat is connected to a counterweight by a long cable and the whole system rotates. NASA studied tethered artificial gravity systems in the 1960s and 70s, but never flew one. SpaceX's early Mars mission concepts included a rotating configuration where 2 starships would be tethered together, but this hasn't been developed. The engineering challenges are significant. Deploying and managing a tether system, dealing with oscillations and vibrations, performing course corrections while rotating. It's doable, but it adds complexity that mission planners have been reluctant to embrace. For Mars surface operations, the 38% gravity is both a blessing and a complication. It's enough gravity to prevent the worst effects of weightlessness. You can walk, liquids behave somewhat normally, and your cardiovascular system has to work harder than in microgravity. But we don't know what prolonged exposure to Martian gravity does to the human body because no one has ever experienced it. It might be sufficient to prevent bone and muscle loss, or it might not. Animals exposed to partial gravity in centrifuge studies show intermediate effects, worse than full gravity but better than microgravity. But these studies are limited. One disturbing question is whether children could develop normally in Martian gravity. If humans establish a permanent colony on Mars and people have babies there, will those children develop healthy bones and muscles? Will their hearts be strong enough? If they're born and raised in Mars gravity, could they ever visit Earth, Or would full gravity be too much for their bodies to handle? We have no data on this. It's completely unknown territory. And the ethical implications are profound because you'd be bringing children into existence in an environment that might permanently limit their physical capabilities. Genetic engineering is occasionally proposed as a solution. What if we could modify human genetics to make people more resistant to radiation, more efficient at maintaining bone and muscle in low gravity, better able to tolerate isolation? The technology for genetic modification exists. CRISPR and other gene editing tools could theoretically be used to give people traits that make them better suited for space. But we're nowhere near understanding human genetics well enough to do this safely, and the ethical questions are enormous. Would we be creating a separate subspecies of space-adapted humans? Would those modifications be heritable? What unintended consequences might arise? Some scientists have speculated about what a Mars-adapted human might look like. Larger eyes to capture more light in the dimmer sunlight, denser bones and more efficient muscles, enhanced DNA repair mechanisms to cope with radiation, different metabolic pathways optimized for the nutritional constraints of a Mars diet. But this is science fiction at the moment. We don't have the knowledge or technology to engineer these changes. And even if we did, society would have to grapple with whether it's ethical to modify humans for off-world colonization. In the near term, crew selection and training are the primary tools for managing biological and psychological challenges. You select people who are physically healthy, psychologically resilient, highly trained, and deeply motivated. You screen for genetic predispositions to conditions that might be exacerbated by space conditions. You train them rigorously for years, simulating mission conditions as much as possible. You build teams that work well together and have complementary skills. And you accept that even with the best selection and training, there will be health problems and psychological challenges during the mission. Medical capabilities on a Mars mission are necessarily limited. You can't bring a hospital. Weight and space constraints mean you're carrying a limited set of medical supplies and equipment. The crew needs training to handle medical emergencies because there won't be a doctor on every mission. And even if there is, one doctor can't cover every specialty. What if someone needs surgery? What if there's a dental emergency? What if someone breaks a bone in a way that requires orthopedic intervention? Telemedicine will be crucial. Doctors on Earth can provide guidance via delayed communication, walking the crew through procedures using video and detailed instructions. The medical AI systems we discussed earlier can provide real-time support. But there are limits. Some procedures require specialist expertise and hands-on skill that you can't replicate remotely. If someone has a medical emergency that requires capabilities beyond what the crew can provide, they might die. That's a harsh reality that astronauts have to accept when they sign up for the mission. There's also the question of medical privacy. In a small crew where everyone is monitoring everyone else's health, how do you handle sensitive medical information? If someone develops a psychological issue, does the rest of the crew need to know? What if someone has a medical condition that might affect their ability to perform critical tasks? Balancing individual privacy with crew safety is difficult in such a confined environment. Pregnancy is another consideration that mission planners need to address. What if someone becomes pregnant during a Mars mission? Space agencies have policies against it, but humans are human. If it happens, what do you do? The fetus would be exposed to radiation and microgravity during development, which could cause serious problems. Birth in partial gravity has never been attempted. The medical risks would be enormous. Most likely, mission protocols would prohibit sexual relationships that could lead to pregnancy, and crew members would be required to use contraception. But enforcement is another matter. These biological and medical challenges are why some experts argue that Mars missions should initially be short duration, with the crew returning as soon as possible to minimize exposure to harmful conditions. You land on Mars, do intensive exploration for 30 to 90 days, then launch and head back to Earth. The total mission time might be only 18 months instead of 3 years. You accept that you can't explore as much, but you reduce the risk to the crew. Others argue that if you're going to make the enormous effort and expense to get to Mars, you should maximize science return by staying longer. It's a fundamental trade-off between risk and reward. Let's talk about the geopolitics, because Mars exploration doesn't happen in a vacuum. Every decision about who goes, when they go, and how they get there is shaped by international competition, national prestige, economic interests, and political calculations that have nothing to do with science. The first human footprint on Mars will be as much a political statement as a scientific achievement, and the country or entity that puts it there will gain advantages that extend far beyond bragging rights. Start with China. The Chinese space program has been methodically working through the milestones necessary for Mars exploration. They've developed heavy-lift rockets. They've demonstrated precision landing on the Moon. They've built and operated a space station. They've announced plans for a crewed lunar landing by 2030. And they've explicitly stated that Mars is a long-term objective. The Tianwen missions are the foundation. Tianwen-1 successfully put an orbiter and rover on Mars in 2021. Tianwen-3, planned for around 2028 to 2031, aims to return samples from Mars before NASA's Mars Sample Return mission. If China succeeds in returning samples from Mars first, it's a symbolic victory with real consequences. It demonstrates technological capability and organizational competence. It shows that China can accomplish what the United States has been trying to do for years, and it positions China as the leader in the next phase of space exploration. This matters geopolitically because space capability is a proxy for technological sophistication, economic strength, and national power. Countries that can operate in deep space are countries with advanced engineering, robust industrial capacity, and the resources to undertake ambitious long-term projects. The United States dominated space exploration for decades, but that dominance is no longer assured. NASA's budget has declined as a percentage of the federal budget since the Apollo era. From a peak of about 4% in the mid-1960s, NASA's budget is now less than 0.5%. In absolute terms, NASA's budget is about $25 billion, which sounds like a lot until you compare it to what would be needed for a human Mars mission. Estimates range from $100 billion to $500 billion, depending on the architecture. That's multiple years of NASA's entire budget dedicated to a single program. Congress has been reluctant to commit to that level of funding without clear public support, and public support for Mars exploration is lukewarm. Polls show that Americans think space exploration is important in the abstract, but when asked whether they'd support increased taxes to fund a Mars mission, support drops significantly. People want to go to Mars, they just don't want to pay for it. This creates a political problem. Politicians won't champion expensive programs that don't have strong constituent support, especially when there are pressing issues on Earth like healthcare, infrastructure, and education competing for the same budget. China doesn't have this problem. The Chinese government can make long-term commitments without worrying about election cycles or public opinion in the same way democratic governments do. If the leadership decides Mars is a priority, resources are allocated and timelines are set. This gives China a structural advantage in undertaking projects that require sustained investment over decades. It's the same advantage that allowed China to build high-speed rail networks, develop renewable energy infrastructure, and fund other large-scale initiatives faster than Western democracies. But China also faces challenges. Their space program, while impressive, still lags behind the United States in some areas. China hasn't done a crewed mission beyond low Earth orbit. They don't have operational experience with nuclear propulsion or large-scale cryogenic propellant systems. Their life support systems are less mature. These are solvable problems, but they require time and investment. The question is whether China can close the technology gap and pull ahead before the United States and its allies launch their own Mars missions. Europe is taking a different approach. The European Space Agency has focused on robotic missions and international partnerships rather than attempting independent crewed exploration. ESA has been a key partner in Mars sample return, developing the Earth Return Orbiter that would capture samples in Mars orbit and bring them back to Earth. ESA also contributes modules to NASA's Artemis program, which is focused on lunar exploration but develops technologies applicable to Mars. The European strategy is to be an indispensable partner rather than a solo competitor. This leverages limited budgets by sharing costs and risks while maintaining technological expertise. Russia, once a space superpower, has fallen behind. Economic problems, corruption, and brain drain have weakened Roscosmos. Russia's space program is largely focused on maintaining existing capabilities like Soyuz launches and ISS operations. Ambitious plans for lunar and Mars missions have been repeatedly delayed or scaled back. The war in Ukraine has further isolated Russia from international space cooperation. It's unlikely Russia will be a major player in Mars exploration in the coming decades unless there are significant political and economic changes. India is an emerging player. The Indian Space Research Organization has demonstrated impressive capability with limited budgets. Their Mangalyaan Mars orbiter, launched in 2013, was one of the cheapest interplanetary missions ever attempted, costing only about $74 million. India has announced plans for more ambitious Mars missions, including sample return and eventually crewed missions, but these are long-term aspirations. India's space program is constrained by budget limitations and competing priorities, but they're building capability methodically, and they shouldn't be underestimated. Japan, with its expertise in robotics and precision engineering, is focusing on niche contributions to Mars exploration. JAXA, the Japanese space agency, is a partner in Mars sample return and is developing technologies for sample collection and analysis. Japan's approach is similar to Europe's: contribute expertise to international missions rather than attempting independent programs. The United Arab Emirates has entered the Mars game with the HOPE orbiter, which arrived at Mars in 2021. This is part of a broader strategy to develop space capabilities and diversify the economy beyond oil. The UAE is investing heavily in space technology and education, positioning itself as a space hub for the Middle East. They're not attempting crewed missions, but they're building infrastructure and expertise that could support future exploration. Private companies add another dimension to the geopolitics. SpaceX is explicitly planning to send humans to Mars independent of NASA, though realistically they'll need some level of government support and partnership. If SpaceX succeeds in landing humans on Mars before any government does, it would be unprecedented, a private company achieving what was previously the domain of superpowers. This raises questions about sovereignty and regulation. Who has jurisdiction over a SpaceX Mars colony? Are the colonists subject to US law, international law? Do they establish their own governance? Elon Musk has talked about Mars becoming an independent entity, self-governing and separate from Earth. But getting to that point requires decades of development and substantial population, which isn't realistic in the near term. In the early stages, any Mars settlement would be entirely dependent on Earth for supplies, equipment, and personnel. Independence isn't possible when your survival depends on regular cargo shipments from another planet. But the aspiration is there. and it shapes how SpaceX thinks about Mars development. Blue Origin, Jeff Bezos's space company, has a different vision. Bezos has argued that humanity's future involves millions of people living and working in space, not necessarily on planetary surfaces, but in large rotating space habitats. His focus has been on developing reusable launch systems and infrastructure for the near-Earth environment. Mars isn't a primary objective for Blue Origin, though the technologies they're developing could be applicable. This reflects a fundamental philosophical difference. Musk sees Mars as humanity's backup planet, while Bezos sees space habitats as the way to preserve Earth by moving heavy industry off-planet. Other private companies are focusing on specific niches in Mars exploration. Some are developing landing systems, others life support technologies, others ISRU equipment. There's a growing commercial space industry that sees Mars missions as a business opportunity. NASA has been encouraging this through programs like Commercial Crew and Commercial Lunar Payload Services, where private companies compete for contracts to provide specific capabilities. The idea is to leverage commercial innovation and efficiency, while NASA focuses on the most challenging elements. This public-private model is controversial. Critics argue that space exploration is too important and too risky to be left to profit-driven companies. They point to safety concerns, lack of transparency, and the potential for corners being cut in pursuit of cost savings. Supporters argue that government programs are inefficient and overly cautious, and that commercial competition drives innovation and reduces costs. Both sides have valid points. The reality is probably that we need both. Government agencies to fund basic research and tackle challenges that don't have immediate commercial return, and private companies to develop practical systems and operations. Core rights are a contentious issue. The Outer Space Treaty says that no nation can claim sovereignty over celestial bodies, but it's unclear whether this prevents commercial exploitation. If a company mines ice on Mars or extracts minerals, do they own what they extract? Can they sell it? The United States passed the Commercial Space Launch Competitiveness Act in 2015, which grants U.S. citizens rights to resources they obtain from asteroids and other celestial bodies. But this is U.S. domestic law, not international law. Other countries might not recognize these claims. Luxembourg passed similar legislation and is positioning itself as a favorable jurisdiction for space resource companies. This creates a potential legal patchwork where different countries have different rules, which could lead to conflicts. Imagine a scenario where a US company and a Chinese company both claim rights to the same ice deposit on Mars. Who adjudicates that dispute? There's no international framework for resolving such conflicts. The United Nations Committee on the Peaceful Uses of Outer Space has been discussing these issues for years. But reaching international consensus is slow. Military considerations are another layer. The Outer Space Treaty prohibits placing weapons of mass destruction in space and limits military activities on celestial bodies. But Mars missions will use technologies that have military applications. Launch systems that can put heavy payloads on Mars could also deliver weapons anywhere on Earth. Nuclear propulsion developed for spacecraft could inform weapons programs. Surveillance and reconnaissance technologies developed for Mars exploration could be used for intelligence gathering. This is why space programs have always had dual-use implications, and why countries watch each other's space capabilities closely. Some defense analysts worry about space becoming the next domain of great power competition. If multiple countries have the capability to operate on Mars, could they come into conflict there? Could Mars become contested territory? The treaty prohibits it, but treaties can be abandoned if countries decide their interests require it. Most experts think conflict on Mars is unlikely in the near term simply because it's so hard to get there. The logistics of fighting a war across interplanetary distances are absurd. But as capabilities improve and presence on Mars increases, the potential for conflict might grow. There's also the question of what Mars exploration means for international cooperation versus competition. The ISS is often cited as a model of international cooperation, where the United States, Russia, Europe, Japan, and Canada work together on a shared facility. But ISS cooperation happened in a specific political context after the Cold War, when both the US and Russia had reasons to collaborate. The current geopolitical environment is more competitive. Relations between the US and China are strained over trade, technology, Taiwan, and other issues. It's unclear whether meaningful cooperation on Mars exploration is possible in this context. NASA has been explicitly prohibited by Congress from cooperating with China on space projects without special authorization. This is due to concerns about technology transfer and espionage. China is developing its space capabilities independently, and they've been building partnerships with other countries, particularly Russia and nations in the global south. There's a possibility of parallel space programs emerging, a US-led coalition including Europe, Japan, and other allies, and a China-led coalition including Russia and other partners. This would be a new kind of space race, less about getting somewhere first and more about establishing competing systems of presence and influence. Mars exploration also intersects with Earth-based concerns in unexpected ways. Climate change, for example. Some critics argue that spending hundreds of billions on Mars missions is irresponsible when we should be investing in solving problems on Earth. Why terraform Mars when we need to prevent Earth from becoming less habitable? The counter-argument is that the technologies developed for Mars, particularly in life support, renewable energy, and closed-loop resource management, are directly applicable to sustainability challenges on Earth. Also, the scale of investment in Mars exploration is tiny compared to what's needed for climate action. NASA's entire budget is less than what the US military spends in a month. We can do both. Income inequality is another concern. Should society invest in sending a handful of people to Mars when millions are struggling with poverty, lack of access to healthcare, and inadequate education? This is a values question more than an economic one. The resources dedicated to space exploration are a small fraction of global GDP. The real question is what we prioritize as a society and what we believe is worth investing in. Some people see Mars exploration as the ultimate luxury, something to pursue only after all earthly problems are solved. Others see it as essential for long-term survival and an inspiring goal that drives technological progress and human achievement. Public perception varies widely by country and demographic. Younger generations tend to be more supportive of space exploration than older generations,